Okay. Morning. I think we're recording here. Yeah, we are. Okay. I'm going to spend a little bit of time going over some of the free response questions for the gases AP questions. Most of these are not too bad once you get going with them. This first one here, number 14, this is a tough one. So I'm going to go through this one in a little more detail, and then I'll get you going on the other ones, and hopefully those won't be too difficult for you. So this one right here, what we have to begin with is a gaseous hydrocarbon. Okay. So what that means is a hydrocarbon, by definition, it just has carbon and hydrogen in it. Okay. So we don't know exactly what it is, but we know that it's some CXHY compound, something like that. Okay. We don't know exactly what it is. It gives us a pressure, it gives us a temperature, and a volume, and they're asking us for the number of moles. So letter A there is pretty straightforward. We're just doing PV equals nRT on that one to figure out the number of moles of the hydrocarbon we have in the vessel. And that's going to come back into play a little bit later in the problem. Okay, so then, and I have the answers up here so that you can kind of see how we're, what our end result is. So B here, it says O2 is introduced into the same vessel containing the hydrocarbon. After the addition of the O2, the total pressure is 1.4 atmospheres. Calculate the partial pressure of the O2. All right, so, I mean, pretty straightforward. The only two gases at this point that are in the mixture are the hydrocarbon, which has a pressure of 0.2 atmospheres. And then we know that the total pressure now is 1.4 atmospheres after we add the oxygen. So the oxygen must be accounting for the rest of the pressure. So you just subtract those two and you get 1.2 atmospheres for the pressure of the oxygen. Okay, here's where it gets a little more tricky. What happens here is basically a combustion reaction. So in this combustion reaction, you've got the hydrocarbon, the CXHY, and the oxygen is sparked now so that we have a combustion reaction happening, and it makes CO2 and H2O. We're assuming that a complete combustion occurs here. And it's telling us what the partial pressures of these gases are, 0.6 atmospheres and 0.8 atmospheres for each of those two gases. And then it also says there's a little bit of O2 remaining in the container after the reaction is complete. Okay, so this is kind of important. What this is telling us right here is that the hydrocarbon itself is the limiting reactant. That's going to completely react, completely be used up, and that's going to come into play a little bit later. So use the partial pressures of the CO2 and the H2O to calculate the partial pressure of the O2 that gets consumed in the combustion. Okay. This is where it gets a little bit tricky because we don't have a balanced chemical reaction for this equation because we don't know what the hydrocarbon is yet. The balanced chemical equation comes down here on part D, but you have to figure something else out before you can even figure out what the balanced chemical equation is. And they kind of have you working backwards on this one. You figure out the equation, the coefficients in the equation, before you figure out what the hydrocarbon actually is, which is strange. That's the part that I've never really seen before. But it's an interesting problem. So essentially what they're doing here is they're telling us the pressure of the CO2 and the H2O. And they want to know the partial pressure of the O2 that gets consumed. Okay, not the pressure that's left, but they want to know how much of the O2 gets used up. Okay, which again is kind of a strange thing to ask, but they have a reason for asking it. So what we're going to do here, I'm not sure if I guess I can just write this maybe over the words here, and it should show up. We're going to have to do PV equals nRT twice. This is probably the easiest way to do this. So I want to find the PV equals nRT of the CO2, okay? And I know that this is in a 1 liter container. It says that at the very top. And this is a rigid 1 liter container, so it's not going to change volume. The volume is going to be constant throughout. Okay, and so I need to do that for the CO2, and then I need to do PV equals nRT also for the H2O. Okay, So I have to do that twice, and I'm going to plug everything else in, and I'm going to solve for my N on both of these. That's going to give me the number of moles of carbon dioxide and the number of moles of H2O that I have. Okay? And so then what I'm going to do, once I have the moles of CO2 and the moles of H2O, whatever my moles of CO2 end up being, then I'm going to set up something like this. I'm going to say, okay, and again, because we don't have a balanced chemical equation, so we have to do this kind of like a combustion analysis. And the thing we have to think about here is that when we have our equation, whatever our equation is, CXHY plus O2 gives us CO2 plus H2O, okay? All of the moles of oxygen that get consumed in this particular reaction are going to end up either in the CO2 or in the H2O. Okay, so if we figure out how many moles of O2 are in the CO2, and we figure out how many moles of O2 are in the H2O, that's going to tell us how many moles of oxygen got used up here. Okay, and then we can go back to pressure. So again, I know that's a little bit strange, but this is the way we're going to do this. So we're going to say in 1 mole of CO2, we have 1 mole of O2. Okay, because if you look at this, the formula CO2, there's 1 O2 in every CO2 molecule. Okay, so that's a 1-to-1 ratio. So however many moles of CO2 we have, that's going to tell us a certain number of moles of O2 that we have. Okay, and we're going to do the same thing for H2O. However many moles we get of H2O from the PV equals nRT up here, then we're going to figure out how many moles of O2 we actually have in there. So moles of H2O, moles of O2. Okay, now this one's kind of tricky. For every, you could do this one of two ways. You could say for every 1 mole of H2O I have half a mole of O2, or I could say for every 1 mole of O2 it's going to take 2 moles of H2O to give me 1 mole of O2, right? Because there's only 1 oxygen in H2O. Alright, so we have, half a mole of O2 in H2O, if that makes sense. Again, this is kind of a tricky problem, okay? So then that's going to give us a certain number of moles of O2 as well. So then we're going to add those together, okay? So whatever we get up here, we're going to add that to whatever we get down here, and that's going to give us the total number of moles of O2. That's going to give us the moles of O2 that got consumed, okay? Because that's the number of moles of O2 that are now in the CO2 and in the H2O, right? Now there's still some, oxygen was our excess reactant, so there's still some extra O2 running around in that chamber now. But all of the O2 that got used to make the CO2 and the H2O, that's what this is going to tell us right here by doing this calculation, okay? So that tells us the moles of O2 that got consumed, okay? But if you look at the problem, it wants to know the pressure, the partial pressure of the O2 that gets consumed, okay? So now that we know the moles of O2 that got consumed, then we can just do one more PV equals nRT here. Okay, and again we have now we have our temperature, same as it was when we figured out the PV equals nRT for the CO2 and the H2O. We know our volume is still 1 liter because it's a rigid container. We figured out how many moles of O2 we have, so we can plug that in, and then we should be able to find the partial pressure of the oxygen. Okay, when you do all of that, you should end up with a partial pressure right here of 1.00 atmospheres of O2. Okay, and then not that it matters that much, but if you compare that to the original pressure, then that kind of tells you how much of the oxygen got used up. It looks like most of it got used up. Okay, so we're going to have 0.20 atmospheres of O2 remaining in that vessel. So if they asked you, now they don't on this one, but if they ever asked you what's the total pressure now in the container, then you could add up the 0.6 atmospheres, the 0.8 atmospheres, and then the 0.2 atmospheres remaining from the excess oxygen, and that would give you your total pressure after the combustion reaction. Okay, so that's going to give you the partial pressure of the O2. Okay, and that's a tricky one. Then what you have to do, and this is even more tricky, I think. It says based on the answers above, write the balanced chemical equation for the combustion reaction and determine the formula of the hydrocarbon. Okay, so what we know right now, we know CXHY. We don't know what the hydrocarbon is, but we know that when we add it to oxygen, it's going to give us CO2 and H2O. Okay. Now the other thing we know here, and we talked about this kind of in reverse in class, we talked about the fact that at constant temperature and pressure, the mole ratio, or I guess I should say the coefficients, equal a volume ratio. Okay. But now we can also say, and this makes sense if you think about PV equals nRT, if we have a constant volume and temperature, which is the situation here, okay, then the coefficients actually tell us a pressure ratio. Okay, and that's good because we don't know a mole ratio of everything, because we don't know how many moles of this. Well, actually, I guess we do know a mole ratio now, because we know how many moles of the hydrocarbon that we had. So you could do this either way, actually. You could use the number of moles of each of those that we found, or you could use the pressure of each of those that we found in order to figure this out, okay? So because I erased all the mole stuff, and because I have the pressure data available to me right now, I'm just going to use that. But again, and I just realized this, you do have the number of moles of the hydrocarbon. That's the first thing that you figured out in part A here. Okay, so you could do a mole ratio here, but what I'm going to do is just a pressure ratio. So I'm going to say the pressure of the hydrocarbon was 0.2. The pressure of the oxygen, and now this is, we have to be careful here. This, we have to use the total O2 consumed, okay? Because there is some excess oxygen here, but remember, in the balanced chemical equation, we're talking about the ideal mixtures to give us exactly what we need, okay? And so if we mix 0.2 atmospheres of the hydrocarbon with 1.00 atmospheres of the oxygen, that's going to exactly, those are going to perfectly react with one another, okay? And then we have 0.6 atmospheres of the carbon dioxide and 0.800 atmospheres of the H2O, okay? And so then, if you look at this, these things actually combine in a pretty nice, neat ratio there, okay? And so what it looks like here is if we divide everything by 0.2, because that's, you can sort of do like a divide by small here to figure out the mole ratio. If we divide everything by 0.2, then that's going to give us our ratio. So this is going to be a 1. If we divide 1 by 0.2, then we get 5. If we divide the 0.6 by 0.2, then we get 3. And if we divide the 0.8 by 0.2, then we get 4. Okay, so that tells us the coefficients in our balanced chemical equation. Now, notice here, in order for this to work, this x right here has to be a 3 so that this coefficient works. Okay, and the h has to be an 8 so that we have 8 hydrogens on this side as well. Okay, so that tells us the formula of the hydrocarbon must be C3H8. Okay, and that's how you get that balanced chemical equation. Now again, you could do the same thing using the moles, the number of moles, and just divide by small there if you're more comfortable doing that rather than using the pressure. But because we're at constant volume and constant temperature, you can use the pressures, and that will give you the coefficients as well. Okay? Then they want you to calculate the mass of the hydrocarbon. Well, now we know number of moles of the C3H8, and now we know it's C3H8, so we can just use the molar mass of this thing to go from moles to grams, right? And then however many grams are in C3H8, that'll give you the mass, okay? And then the last question there, kind of self-explanatory in the answer key, because it talks about how because we've got CO2 in this thing, and when CO2 dissolves in water, it forms carbonic acid, which actually ends up giving up some H plus ions. So that's going to make that solution slightly acidic. Carbonic acid, CO2 dissolved in the mixture, is also responsible for the acidity of soda. So hopefully that makes sense. Okay, on to the next one. So this one right here, this is a molar mass determination here, okay? And this is similar to the experiment that we're about to do today. Today being the Tuesday before break. So here, these first few calculations are not difficult at all. These are just subtraction things, okay? So the mass in grams of the dry air, we've got the mass of the sealed flask in the dry air, and then we've got the mass of sealed flask in the unknown gas. And they're giving us the density of the dry air, okay? So we know the volume of the flask, we know the density of the dry air, so we can figure out, should be able to figure out fairly easily there, the mass in grams. You can do this one of two ways. Let's see the mass. Let me think about this for a second. So we know the mass of the sealed flask in the dry air. We know the density of the dry air. We know the volume of the flask. We don't know the molar mass of the dry air, though. So I think... Let me pause this for a second, because now I thought this was just a simple subtraction, but I got to think about this for a second. I don't want to waste your time on it. Okay, sorry about that. That was simple. I was overthinking it. So we've got the volume of the sealed flask. So we can assume that the dry air takes up the entire volume of that sealed flask, and then they give us the density of the dry air. So all we have to do here, 0.843 liters of the dry air times the density. Okay, so 1.18 grams in 1 liter. So that would give us the 0.995 grams there for the mass of the dry air. Okay, so then we can figure out the mass of the sealed flask itself if it had no air in it. All we have to do here is take this number, the mass of the sealed flask and the dry air, minus this number. Okay, and that would give us the 156.71. Then we can calculate the mass in grams of the unknown gas, because then all we have to do, now we have the mass of the sealed flask right here. So then we just take this number, 158.08, minus the 156.71, and that gives us the mass of the unknown gas. Okay. Then, once we have the mass of that gas, we can figure out the molar mass of the unknown gas. And probably the easiest way to do that one is just to use Dr. T. Well, no, sorry, Mr. T poops violently. So molar mass equals MRT over PV. And we have all of this because we just found the mass of the gas. We know the temperature that it's at, we know the pressure that it's at, and we know the volume of the sealed flask. Okay, so that'll give us the molar mass. That's probably the easiest way. You could use PV equals nRT on this as well. And once you find the number of moles, then you could take the grams divided by the moles. That would also give you the molar mass. But this is, Mr. T poops violently is probably the easiest way to find that one. Okay. Then calculate the percent error in the value of the molar mass. Okay, I think you guys can do that because basically you're just comparing that to the value we found in part D And then I think the rest of this is fairly self-explanatory in the explanations themselves. Okay. Now this next one down here, there's one tricky part on this one. Carefully get down here. Okay. So we've got a reaction here. H2O2 breaks apart to form H2O plus O2 gas. Now here's the tricky part on this one. This is an aqueous solution of H2O2. All right. That means that there is H2O2 mixed with water here, okay? So when it tells us the mass is 6.951 grams, that's not the mass of the H2O2. That is the mass of the entire solution, okay? And it says the H2O2 decomposes completely, okay? But that doesn't mean 6.951 grams of H2O2 decompose completely. It means that however much H2O2 is in there decomposes completely, okay? And so this is a gas collected over water, so we're going to have to subtract the vapor pressure of the water, which that's what they have you do for part A on this one. Okay, so to calculate the partial pressure, you just take the total pressure, atmospheric pressure for that day, and you subtract the water vapor pressure, and that's going to give you 741. Then you're going to calculate the number of moles of O2 that get produced here. You just need to use a PV equals nRT. So once you have the pressure of the O2 here, then you should have everything else that you need. You have the volume right here, 182.4 milliliters. You're solving for N, you know the R, and the T is 23.4 degrees Celsius, which you're going to have to convert to Kelvin. Okay, but that'll give you the number of moles of the O2. Then you can use the balanced chemical equation up here. Once you know the moles of O2, you can figure out how many moles of H2O2 you have, and then you can figure out how many grams of H2O2 you have just using stoichiometry. I think you guys can do that. And notice, 0.497 grams of H2O2, that's a lot less than the 6.951 that we had up here, okay? And so then the last thing that they're asking here is find the percent by mass of H2O2 in that original aqueous sample. So then you just take the 0.497 divided by the 6.951, and that'll tell you what percent of that original solution actually was hydrogen peroxide, and then we can assume that the rest of that solution is water. Okay. All right. This one, I don't think I even need to talk to you about this. I think you're given a certain amount of information. You need to find the molar mass of the compound, and then use that molar mass to find the molecular formula. Now, the one thing that it might be a little rusty on here, if you're given an empirical formula, you want to find the molar mass of that empirical formula. Okay, and then you're going to use the one of the gas laws, and again, the one that I would probably do on this one, since they give you a density, is Dr. T. Poops. Okay, so that's going to give you this molar mass. Then you just need to compare this to this, and usually there's some multiple of one another, and that will tell you what you have to multiply by to get the molecular formula. Okay, I think you're probably okay on that one. And oops, let's go down here. We're almost done. This is the only other one that's maybe a little bit tricky. Okay, so we've got a certain mole sample of ethanol, and all the methanol is vaporized. Now we have to be careful here. Vaporized just means it's turned into a gas. Okay, it goes from a liquid to a gas. And some of that methanol then decomposes to form carbon monoxide and hydrogen gas. Okay, this is an equilibrium equation, which we haven't talked a lot about equilibrium yet, but you don't need to know much about equilibrium in order to be able to figure this out. You're just thinking about the amount of gas in this tank. Okay, so it says the reaction mixture contains 6.30 moles of CO gas, carbon monoxide gas. So we want to know the moles of H2 in the tank. All right, so assuming that we had no H2 in there to begin with, so then all the H2 is coming from the decomposition of the CH3OH. If we have 6.30 moles of this, based on the stoichiometry in the equation, then we should have twice as much of the hydrogen gas. Okay, so that's where this 12.6 number comes from. It's 2 times 6.30. Okay. Then we're going to calculate the number of grams of CH3OH remaining in the tank. Okay, so this is a limiting reactive problem. Okay, so we know, and you can use either one of these numbers. I'd probably just use the 6.30 just because we're sure of that number. Not that you wouldn't, I mean, you're sure of this number now, but if you're working this out on a test, you probably want to use the number they gave you as opposed to the one you calculated, just to be on the safe side. So you'd start with your 6.30 moles of CO, okay? And then you figure out how many moles of CH3OH would need to be used in order to create that many moles of CO, and this is in the stoichiometry here, this is a 1-to-1, okay? So 6.30 moles of CH3OH. Now notice we started with 8.55 moles, so if you just take the 8.55 minus the 6.30, that would give you the number of moles of CH3OH that are left. And then you can convert that into grams using the molar mass of the CH3OH. Okay, and that would give you the 72.1 grams right here. Calculate the mole fraction of H2 in the tank. Okay, now we know the number of moles. We just figured it out actually. So this one right here, 2.25 moles of the CH3OH left. We know we have 6.30 moles of the CO, and we know we have 12.6 moles of the H2. So we know the number of moles of each of the gases we have in there. So then you just take the 12.6 moles of the H2 divided by the total moles, which we can now calculate because we know the moles of everything that are in there. And that's going to give you the mole fraction. Don't multiply by 100 there because that's going to give you a percentage. They just want the mole fraction. Okay. And the total pressure in atmospheres in the tank. Okay, what I would do for that one is just a PV equals nRT. So PV equals nRT, and use the total number of moles, plug that in for N, and that's going to give you the total pressure. Okay. So that's that. And then the average kinetic energies and which gas has the highest average molecular speed. That is pretty self-explanatory. I mean, the explanation kind of takes care of that part. Okay. Let's see if there's anything else we need to talk about here. I think the next free response question is pretty much all hypothetical or theoretical. Not a lot of calculations here. Yeah, there's no calculations on this one, so this is all, I think, pretty well explained in the actual answers. So, okay, I think that's it. Hopefully that helps with the free response questions. A couple of those are kind of tough, but if you guys know what you're doing on that, I feel like you should have a pretty good understanding of how to use the gas laws in pretty much any situation you're going to encounter on an AP exam. So, good luck studying. I guess we'll see you after Thanksgiving break.